this whole effort started in March when we were also concerned, 2020, when COVID came, and we asked ourselves what we could do given our training. And then we saw all these projections coming from Neil Ferguson that millions of people will die in the US, in Europe. So then we looked further and found that he was doing Monte Carlo simulation. Now that's something we are familiar with. So we thought we can try and do that here. And then somebody said, okay, you should talk to Gautam Menon and see what's going on in the state of India on COVID modeling and whether this makes sense. And Gautam mentioned that Rajesh is already doing this COVID modeling, building a simulation model. So we got in touch with Rajesh. So Gautam was quite discouraging at that time about us starting this effort. I don't know if you changed your mind since then. We'll find out. We'll see. But so Rajesh and my colleagues in TFR and some of our students tied up, and we had intensive interaction for a month and a half where we built this simulator. And this was in C++. It was cutting edge, very fast simulator. It compared well with other people we spoke to worldwide. So it was kind of good in that sense. So slowly Rajesh moved on to Sero survey in Karnataka. I was doing Sero survey in Mumbai. All of us kind of dispersed. Daksh Mittal joined me around July, August. He's a BTech, then he was in civil services. He wanted to come back to research. So that's so then basically it was he and I who kind of spent a lot of time working on some of the issues that I'll talk about today on Mumbai modeling. And our interest is very quickly veers towards algorithmic issues. So I'll talk about that as well. Although today I will not spend that much time on it. I'll give you a flavor of what we do in that setting. But I'll just tell you things that we did for Mumbai through our COVID modeling. Shubhadra is my PhD student, so she also was involved, but she also had a PhD to do. Daksh was more full time on this. So my outline is fortunately I'll save time here, so I won't tell you much about the agent-based simulator. Everything that Gautam told you and that Madhav told you is kind of incorporated in this, so you can just assume that to be, I'll assume that you know that. And I'll talk about some of its successes and the failure, and the failure is not capturing the delta wave. I think pretty much everybody who didn't say anything or said something was wrong. So, that's a failure of everybody. What can you do? Just that we should be more aware that these things can happen. And so that's the whole point. What did we learn from that? So that's how do we go forward after seeing that? So I'll talk about what we had to say about the second wave, about the potential third wave and the third wave. Given that we were learning as we kind of went along, we're not really experts in this area. Key drawback of all of this was early on our model was very fast. You're simulating 2-3 months of COVID. It did it quite quickly. But now we are doing 2 years of COVID modeling, and each simulation is taking 13-14 hours. 13 million people of Mumbai, each and every person is being simulated, what they do, what they don't do. We are respecting privacy by not giving them names. So there's a lot of effort going on, and each run takes 13-14 hours. You're doing many runs. So it's enormous amount of time. So you have to ask yourself, how do we reduce this computation time? So that went into developing a deeper, so let me just talk about this right now because I won't get time to talk about the mathematics later. Deeper understanding of the underlying probabilistic structure of the simulation model as well as COVID itself. So, so initially this COVID, as it spreads in any city, it's like a branching process. For those of you who know what a branching process is, it's like there's a parent who stochastically randomly has some children. Each other child randomly has a few more children, and that's how the process evolves. Children can be of multiple types. There are happy children, there are sad children. So in this case, the COVID, the infection can be, somebody is very symptomatic, somebody is highly infectious, somebody is old, so they kind of infect further. They get affected more. So all of these are kind of multiple type of things, but nonetheless, it's a branching process early on. And thereafter, once there are enough infections, all the randomnesses occurred already. And the randomness is nicely captured in a branching process just by a single random variable, the intensity of the branching process. It's a very nice property of a branching process that intensity is random, it depends on the sample path. But on any intensity, the proportions amongst the different types of children stabilizes very quickly. So what that means is that proportions have stabilized very quickly, so we can actually shift from one time period to another time period without worrying about the fact that the initial distribution has changed. Initial distribution is more or less same, it's stabilized. So that property we can use. Thereafter it's mean field, so it's going to evolve deterministically. So it's like a massive compartmental model, but in some sense you can't really solve a million compartmental model. You need a stochastic simulator to simulate it for you. So that's the utility of simulation at that time. So we'll talk about how to, that's what we did basically. We came up with a shift, scale and restart features. So the point was we asked ourselves, how do we get output from this 13 million simulator for Mumbai using a 1 million simulation model? And the key insight was early on 1 million model, 13 million model with same number of infections evolve identically more or less. It's just a few people who kind of infect, they're seeing people who are not infected in both the models. So they evolve identically. Thereafter, as I mentioned, the proportions have stabilized. So whatever is happening in 13 million model, so suppose 13 million model has some X number of infections, then you go to the 1 million model where you had X by 13 number of infections. At that time, X by 13 in the smaller model is same as X in the larger model. So I'll just follow the smaller model from that time. I'll shift its path to when it becomes, X in the larger model, and I'll scale it by 13. So everything I see thereafter is just a scaled version of what I see in the smaller model. This combination lets me use a smaller model to generate a complete sample path of the larger model. So I never have to go to the larger model to see what would happen with the larger model. So that's the flavor of what we do here. I'll just give you a very brief flavor of this here. The papers are up so you can kind of see the details there. So this was shift, scale, and restart smaller models. We still, this smaller version of this appeared in this. Then there are other papers. Our largest effort was with Rajesh and his team and my colleagues and TFI and students. This is a 19-authored paper, Journal of the Institute of Science, and then some others. Our model, our operational model was that we used to do a bunch of experiments trying to understand the situation, prepare a small report, submit the report to the BMC and other Maharashtra government folks, let them know what we are doing, and then also keep the newspapers informed. So that's kind of how we proceeded. So I'll tell you about our findings. That also limits the amount we can we can rewrite history here. So we have to stick to what's already been written. Okay, so I'll skip this agent-based simulator. Just suffices to say that, Mumbai has all these buildings and these dense slums. It's very difficult to capture them well with the aggregate SIR type model. Detailed models are very useful to capture this kind of heterogeneity. And this is to say that people are living in one place and they're working in very different places. So there's a lot of transportation going on. So all of that also needs to be captured. So detailed model is good at capturing all of this. In Mumbai, in normal times, 8 million people travel on train each way. So that's a huge super spreader event when it takes up. So one needs to try and capture that as well. All right, agent-based simulation, all the nice details that we've been talking about. So we create demographics, employment, geospatial data for each locality, slums, non-slums, all that is matched to whatever census available data is available to us through a variety of sources. Age is matched to the actual city, household sizes, workplaces, school size distribution, urgent destination matrices for commute pattern, details of transport usage, and later on, when you start introducing vaccines and you have variants, these micro models allow you to, model these things fairly accurately. So we did all of that in our model. So big picture, I'll just say one slide on the simulation model. Initially, you have the synthetic city which matches the actual city in this aggregate details. You seed the city with initial infection at time 0. And I think Rajesh and we did a lot of efforts and figured out that this corresponds to about February 13th, 14th in 2020, when you have about 100 infections in non-slums area in Mumbai. So we randomly start with that. Next step is compute exposure rate lambda nt for each susceptible person. So we'll go through each and every susceptible person every 6 hours. We'll find out that susceptible person is, is living in this household. So in this household, so many people are already infected. This is the infection rate coming to it. This person lives in this community, and this many people are infected in this community. So this is the infection rate coming to it. This person goes to this workplace, so on and so forth. So we compute the overall infection coming to each and every person. And then you just flip a coin. You flip a coin, and with that probability, the person gets infected, exposed basically, or not. And that's how the simulation kind of continues. A person who's gotten exposed will now, after some random time based upon the data that we have, will become infected. With some probability, the person will become symptomatic, again matching the data. If the person is symptomatic, depending upon their age and other characteristics, maybe comorbidities, although we didn't explicitly model those, the person then becomes hospitalized. They stays in the hospital for so long, becomes critical, may survive, may not survive. All of those details are modeled basically. So you do a best guess in all these things. So this is an example of how we fit information for this progression of disease for each individual. So I won't spend too much time on this. Now, lockdowns, case isolations, all these interventions that are done over time. So for Mumbai, we were tracking these things very closely at that time. All of this means restriction in movement, basically, right? That's the attempt. You restrict movement of people. Because you restrict movement, so suppose you restrict my movement to community, now I don't go to community that often, so the community rate that was coming to me gets reduced. So when I flip a coin, I get much lesser kind of COVID infection coming to me. So that probability comes down. So that's how one captures mobility and reduction in mobility in these models. But by and large, you can be reasonably accurate with these things. The question is, how accurate are you, and how do you kind of build in some accuracy at least? And it's human behavior. How do you capture these things? It's not so easy. So let me give you one picture, and this is a picture worth spending some time on. So these red bars are the fatalities that we saw in Mumbai on a daily basis. Right, these are fatalities. So everybody with me on this? So you can see that we have about 110 fatalities sometime early June. And these were coming down. There were about 50 fatalities a day on November 1st, thereabouts. Right? We fit our model essentially to match this slope. We saw this rising slope in Mumbai, but also in all of India. And again, because it's a branching process, doesn't really matter. The bigger data you take, the better. So you choose your parameters of this transmission rates so that this slope is being matched. Thereafter, there are things like, okay, we are saying that some fraction of population is compliant, so they respect the restrictions that we are putting on mobility. Some are non-compliant, so they are much more mobile than the compliant people are. So you use that lever to match the data here. And this was, as I was discussing earlier, this was something we had missed in our August report. This was a peak, a sudden jump in fatalities. We came up with this August report, and that reporter started calling us that, do you have any idea that there's a festival going on, Ganpati festival going on, and because of that cases are rising. So we learned that. We were completely kind of oblivious to it. So we learned that, but we took it well in the sense that we realized that the bump that you see here can be explained if you increase the community interaction by some small percentage and increase the non-compliance by a small percentage during that period. That explains this bump. It's a good thing because now we can fit this, and thereafter when we have Diwali mixing or Dussehra mixing or Christmas mixing, we have a rough idea how to capture these things. In these models, one should not aim for like extreme accuracy. You just don't want to miss out the elephant. You want to get the big picture right. You don't want to miss a delta wave when it happens. So anyway, I'll come to that in a moment. This is what we did. So this is now mid to late October. Our green line is our kind of prescription that what would happen if you open up the economy in Mumbai on November 1st. The local trains, all the offices, if you open them up. So, so can you open up schools, and what will that mean? All of that kind of stuff. So you'll see a peak basically a month later, around December. It'll be a peak of about this height, and then things will come down. This is, we assume that there will not be any new variant. So it's a reasonable thing to do. The point was at that time we thought that this kind of pain is acceptable because it's not clear if the vaccines are going to come, how effective they are going to be, when they will be delivered. So it seemed like it's something that, given that pain that we were obviously aware of, people are not getting employment, they can't go to work, there was so much suffering, children were not going to school. It seemed like this would be a good idea. So this was our recommendation. But then we did one more scenario with this orange line where we said what would happen if you open the economy instead on January 1st. So if you open on January 1st, then your fatalities will start to show. This is all fatalities, by the way. We're only focusing on fatalities, as you may know by now, because that's a much more reliable data than all the caseload data, etc. So you see in this case, if you open on January 1st, cases, fatalities will start rising around February 1st, thereabouts. You'll have a small bump. It's kind of interesting because what happened then, so let me just go step by step on this. So this is what actually happened. This is fatalities that were actually observed till February 1st. So we heard that you should not predict more than 2 or 3 weeks. But you could see here that we were actually quite accurate all the way up to February 1st. What you see is that the orange line, which predicts fatalities till February 1st, is, it's underestimating the actual observed fatalities. But this is easy to explain, which we would not have been aware of at that time in our modeling, that as the cases start to drop, as the fatalities start to come down, people's behaviors becomes more lax. So once you incorporate that, you can actually match this quite well. And we are thinking to ourselves, okay, these models have enormous predictive ability. It's actually quite useful stuff. Part of it also is that Mumbai is a very crowded and small place. So it's an easier problem to solve in some sense in Mumbai. You probably can't do the same thing in Delhi or Bangalore. Once the disease takes off, it does kind of affect whoever it can affect, by and large. So you get things right this way. So this is what we had done, and by this time things looked like they were working out quite well. Whatever we could not measure, forecast, we could explain. But it also confused things for us because when the Delta variant happened, we expected this peak here. So initial first few weeks, we thought, okay, this is exactly as we anticipated. When you open up, you will see these cases. By February 3rd week, we thought things are not what they should be. It looked like it's very, very confusing. I think the person, if you want to see, I think Murad Banaji was one very active on Twitter. He's a person who's pretty much always on the ball. So was Gautam, but Murad maybe a little bit even earlier. He was warning us even that this is something very serious going on. So we kind of became worried around second, third week. It's important, this timing, because that's the best you can do in these in cases where you cannot predict the environment. You should be nimble enough to change and adjust to it. And I think in March first week or so, a lot of people there was some genomic data also coming out to support that there's a new variant which is more infectious perhaps. But nonetheless, political rallies continued. So I mean, a more nimble system would have responded better. Okay, so this is what actually happened under Delta wave here. And now we're not trying to forecast this. This effort is now to just fit the model. A lot of people fit the model, but they say they forecasted it. We can't do that now. We've already documented, we push ourselves in the corner by not being able to say this. But anyway, jokes apart, the point is this, that, so we saw this in February 1st, the fatalities remained low all the way till mid-March or so, and then they began to take off. And then there was a very steep rise, right? So now we are wondering what is going on. How do we understand this? And in particular, does our mathematical model have anything to say in this kind of setting? So what we tried was, we tried about 40, 50 different scenarios. Time, these are all time consuming, so one couldn't do too much, to try and understand what's going on here. And let me just say the big picture. I won't go into details. You say to yourself, maybe what's going on here is that people became too lax. They were not compliant. They were kind of just, there was a lot more mobility, and that explains things. But that mobility would have shown up much earlier. Later on, actually, we had started putting in restrictions. So you would not have seen this kind of curve. You can say that maybe reinfections happened and reinfections increased over time, and that explained all this. But there was nothing in the data anywhere coming up which suggests that reinfection was following this very specific pattern. So that would have not done a good job of explaining this. You could say that maybe trains opening up caused some of this problem, but again, all of these things can be ruled out. The only thing that explained this data that we could get to match exactly was if we assume that there's a small percentage, say about 1 or 2% of a variant on February 1st when Mumbai actually opened up, because when it opened up, then opening up and then trains opening up actually becomes a super spreader event. So there's a 1 to 2% variant, and that's about 2.5 times more infectious. That explains this much better. And just to tell you, so this is something we draw a conclusion around late April, and that's kind of the wisdom even now. So in some sense, our computational study was able to capture something which which is closer to truth. But just to tell you that this was not something that we are kind of somehow reading up and kind of fitting to. On April 22nd, I tweeted that we can explain this with a variant which is 4 to 5 times more infectious. Then on April 25th, I tweeted that no, that was wrong. There was a bug in the code. We were not modeling infection the train correctly. Actually, it's 2 to 2.5 times. So that number actually was what we finally were able to make things work to. So this is how we could explain Delta wave. Let me just say a few things quickly. So this is, okay, we are saying that suppose the economy had opened faster than we anticipated, faster than suggested by Google mobility data. We were trying to calibrate all of those things. Then you would have seen something with slopes like this. I think this is reinfections would have given you a slope of some sort like this. We tried a variety of scenarios. The reason I'm showing you this picture is that we tried lots of things. But what's interesting is that although all of these pictures are kind of wrong, they are still peaking at about the same time and coming down at about the same time. So one conclusion you can draw from here is that when the peak occurs and when the trough occurs thereafter, that's a fairly robust phenomenon. Even if your model is substantially wrong, you can say, you can predict these things with reasonable amount of certainty. Yes. Yeah, for Mumbai that was true. So Mumbai was in a very different situation from all the other metros in India, because by February 1st, as per our model and as per a variety of other sources, Mumbai was far more infected than others. So we had about 67% of Mumbai was already infected, and we know that Delta was by and large respecting the immunity that infections gave you. They were actually fewer deaths, yes, yes. I mean, especially if you keep in mind that there was much more under-reporting at this time. And this was, was essentially what happened here was that the slums got wiped out, and they had massive amount of infection. And now it's a much smaller pie, but nonetheless, even if it's 67% infected, the population that is unaffected is older, so they're more at risk. All right, so the point was some things can still be projected. So that's kind of what we did from here. So we said, okay, when will it peak? When will it come down? So those things are, you could say. This is how, as per our model, the variant kind of grew from close to, I guess, 2% on February 1st. It became about 90% by 1st of May or something. This is how our model shows the variant would have gone ahead. This is interesting. This is showing the prevalence of the disease in the population in Mumbai as a function of time, as per our model. The red line is how much percentage of people were infected in the slums in Mumbai. Slums are about 52% of Mumbai, as per census data, probably a little more in reality. This blue line is non-slums. And what's nice about this effort is that, we were involved in the Sero survey for Mumbai in July 2020, where we took some regions, some slums and non-slums, and we found, quite to everyone's surprise actually, the slums had about 56% of population already infected in July 2020, and the non-slums about 15%. So this was very useful. These kind of things are actually quite surprising but useful, because this changed BMC's focus from slums to non-slums. Up till that time, they were kind of going into Dharvi again and again, and there was like cameras everywhere, and everybody was going to see that they're doing such good work in Dharvi. But this actually led to some change in policy. But from our point of view, this was very useful, because now we could calibrate our model on how the infection spreads in slums and non-slums, so that we match these numbers. So on July 15th, we're actually matching these percentages that we observed. And thereafter, I think there was some Sero survey done in October, which found that slums were 75% infected, and that's the kind of number that we were also seeing in our model. So there were a lot of places over here where the numbers we had were not too far off from what Sero surveys were revealing. So 80% was a number that was kind of doing the rounds around March, April. It's not too far from what we were seeing here. Okay, so this is what we had here. So then we said, okay, what can we do? It looks like, we can only do very limited things with the computational model. So for the third wave, because by now everyone is terrified with what we saw in the second wave, and in particular, will we have enough oxygen ready when the third wave strikes? That's a huge worry for everyone. So what we did was that we realized that we don't really know what's going to happen going forward, and we should not even attempt to kind of say something concrete. We'll just do massive scenario analysis. What if there is reinfection? What if there is a new variant? What if the new variant is more virulent? What if the vaccines are only mildly effective? What if they have mild coverage as opposed to being extensively delivered? So in all of these cases, what happens? And the thinking was, let us at least look at the peak fatalities that we see in each and every case, because then you can put everything in one picture and it helps the policy makers to see, to get a sense of what to worry about. So this is the picture here. In June 2020, we saw the peak fatalities of 110. In May 2001, the fatalities were about 90. And these are a variety of scenarios that we do. I won't get time to go through these scenarios, but it was kind of, like I said, all the dimensions that I said. The big picture was that even in the worst case, which seemed to us to be a worst case at that time, which is reinfection of 10% of population. So 10% of the population which has already been infected suddenly becomes susceptible again. Vaccine coverage is poor, just vaccine efficiency is 30%, and I guess there's high amount of intermixing. We expected the same amount of fatalities as we saw in the Delta wave. So not much more than that. Now, in this case, I guess we are looking at, sorry if I can see this correctly. I think that this was also when you have a new variant which was about 50% more infections than the Delta variant. We thought that was kind of a pretty worst case thing. But nobody anticipated that Omicron would be even much more than that. It was 2 times more than even Delta variant. So, all this worst case analysis, pessimistic analysis is also so limited. But nonetheless, the point was that, it looks like we don't have to get too worried about if we have oxygen at the same level as we had during the Delta wave, or somewhat more than that, then we look like we're in a reasonable shape, unless something dramatically different happens. So that's the kind of things we did. This was actually and then we said, okay, if nothing dramatic happens, no new variant happens, reinfections remain mild, then you'll see fatality profile, which looks like this going forward. And this by and large held out till Omicron came. This, different peaks are just because different vaccine efficiency. But if vaccines are effective and they are widely distributed, then you will see smaller peaks, which is kind of what we saw in Mumbai. So in that sense, these models were not terribly off. And then when Omicron came, so again, we didn't really have much data to go on, but by mid-December, data from South Africa was concretizing. So a reasonable thing seemed like, okay, 35% of people who are infected will be amenable to reinfection. The Omicron itself is about 2 times more infectious than Delta variant. So with that, we did some quick simulation, and at this time we realized that you really can't be precise about cases or fatalities, but you could say when the disease will peak. So I think on January 4th, we had said that the peak will be between January 6th and 13th. So all these things, whatever we were seeing was also being reported to newspapers. In this, we were somewhat accurate because I think most people were saying that Omicron would occur in 3rd week of January. It would peak in mid or 3rd week of January. Doesn't matter. I mean, in this setting, there's no policy implication for what everybody was saying. It's just, our curiosity, were we getting it right or not. All right. So key drawback, as I mentioned, was that the time taken to run the city. So can a smaller city with same homeschool workplace structure give us correct answers? That was always troubling us. To me, this was something which took us 90% of our time in terms of just how much time we spent in trying to understand what's going on. This was because it was algorithmic, so it was interesting for us. So this picture is interesting. I'm looking now at the case where there are no interventions, no lockdowns. So it kind of also, we had this discussion about lockdowns were useful or not useful. This kind of tells you what would have happened if there was no lockdown at all, which is a strong counterfactual situation. You would have seen high amount of, and this is number of people getting exposed right now. But so blue line is what the larger model would say would happen in a 13 million city. And orange line is I run a 1 million model right from the beginning. I just multiply the output by 13 times. Just scale the model basically. This is both these models are starting with the larger model is starting with 100 people in the beginning, and the smaller model is starting by so larger model is starting with 128 people in the beginning, and the smaller model is starting with 10 people in the beginning. And the point is, if you start with 10 people, you underestimate the peaks. So the point of this picture is simply that simple scaling, you don't expect simple scaling to work, but it's just confirming that simple scaling will underestimate the peak fatalities, peak cases that you see. So this is what we saw then, and then we tried this experiment. This is the time when we didn't understand the probabilistic structure at all, so we're just playing around. So this is a case where we started with 100 people in the million city and 1,280 people in the 12.8 million larger Mumbai city. So you start them with more number of people in the beginning, and then you see that scaling actually works. And now in this case, we start with, I guess, 1,000 people in 1 million city and 12,800 people in the larger city, and then it's a perfect match. So it's telling you that if you started with enough people, then then the scaling actually works perfectly. It's quite surprising at that time to us. That and this is in a realistic model. So this is another interesting chart here, that up till 35 days, if you run both the smaller model and the larger model with same 100 number of people infected in the beginning. So identical conditions, smaller model and the larger model, they show exactly the same kind of output. So this is number exposed, but I could have plotted number infected, number hospitalized. You would have seen similar matching of curves. So up till 35 days this happens. And by 35 days, that's like the log of n divided by log of rho. Rho is the exponential rate at which the population increases in the initial phase. So basically, it's a time at which the number infected become a non-negligible fraction of the number of the population of the system. So before day 35, the number infected is a negligible fraction, mathematically speaking. If you have n as a population, rho is the rate at which the population is growing exponentially. So till that time, they remain together. After this time, what's going on is that the smaller model is seeing far more double hits. It's hitting more people who've already been infected compared to the larger model. Hence, you see the kind of underestimation of peak. Okay, so with these insights, this is our proposal, which is that you run the smaller model. So what I'm telling you now is, how do you run just the smaller model and get the output from the larger model from it on all time scales? So you run the smaller model for 35 days. At day 35, you see how many people are infected. Suppose that turns out to be 50,000. Right? Then you find the time at which you had 50,000 upon 12.8 people infected. That suppose turns out to be day 20. So all I'm saying is that on day 20, I have 12.8 times less people infected in the smaller model compared to the larger model. If I scale this, I get this value. So what I'll do is I'll use the smaller model path till day 35, and I'll take this path from day 20 onwards, right here, and stitch it onto day 35. And now this smaller model output exactly matches the larger model output. And the reason is, when I'm shifting across time from here to here, the underlying distributions are not changing because it's a branching process which quickly stabilizes in proportions. So that's enormously helping us. The proportions are stabilized. So that's why this works out. And then you say to yourself, okay, now this was the case where there was no interventions. So there are no restrictions on mobility. But suppose in a realistic setting, on day 45, restrictions were imposed. So this corresponds to about March 20, March 22 for actual Mumbai. That's when the lockdown was imposed. So that's about 10 days after day 35. So how do I, in my smaller model, how do I impose these restrictions at the right time? So what I'll do now is, on the day 20, I'll restart my simulation. On day 20, this is going to correspond to day 35, but I'll start intervention 10 days later. And this path, with the interventions, I'm going to patch up with day 35 here. So all I'm saying is, earlier I was doing day 35 with the smaller model and patching up whatever happened after day 20. I'll do the same thing here, but on this day 20 path, I'll introduce interventions after 10 days. So in the actual model, the interventions happen on day 45. So I'm matching the actual model day intervention, and then you get a complete match. So this is the big picture. Now there are small nuances, but the nuances are small, and maybe we can take them up in question answers. But this was our idea, and this is our actually a complete match between big and smaller model with realistic model, realistic interventions, lockdowns, case isolation, all those restrictions up till day 250. I don't have a picture, but you get a similar match up to day 450 as well. So it's quite a good match. So it's quite workable in that sense. So let me stop here. Theoretical support would be, I'll just look at this whole problem mathematically in an asymptotic regime where the population n goes to infinity. And then I'll use results from branching process theory, which says, okay, what happens to the branching process as n goes to infinity? Then I'll say that, okay, after some time, my underlying stochastic process follows a mean field process, so meaning normalized by the overall population, it's converging to something non-trivial. So if something which is 13 million sized and normalized is converging to something non-trivial, and something which is 1 million sized and normalized converging to the same thing, then 13 million and 1 million are related to each other by factor 13. So that's kind of the idea. So that's how I get everything to match out. Okay, let me just say one thing very quickly before I end, because this you might like. We don't understand this. This is, R of t is at time t, person gets infected. How many infections does that person have? How many infections? How many children does it have? Which can be attributed to that person. So as a function of time, in my simulation model, I can measure these things. Now, in my slums are much more infectious than my non-slums by a factor of 3 actually. That's how we modeled it, right? Turns out, so this, this red line is for slums and this green line is for non-slums. turns out that initially these R of T's differ between the two, but after some time, once the shocks are kind of absorbed and softened up, they actually move identically together. As I have interventions, this R of T between slums and non-slums equalizes and stays equal. So very strange phenomena, needs mathematical proof. Why should it be that a person in slum is infecting the same number of people on average as a person in non-slums? Because that kind of tells you that, okay, slums and non-slums is just two ways of dividing the population, but no matter how the population was divided, this R of T is stabilizing across population. What's nice is that means that I can just sample a small subset of population and find R of T of there, and that will hold for the whole population. So that's the utility of this thing. But this is something we observe by simulation. We don't really have a mathematical understanding of this. Let me end with this. Thank you.
Questions? In these histograms you showed of the number of fatalities in this model, there are secondary maxima that go up and down. Now the rates they're all exponential functions to start with, right? They're just decreasing exponentials. The lambdas that you have, the lambda sub n, yeah, this picture for instance. Are these peaks on the same scale? They're on the same. Yeah.
That suppresses the rate.
Right.
So that's why this actually starts to come down. Now at this point, suddenly, because of there was increase in interaction because of festival season, then this went up again.
What I understood was that the secondary peak is due to another variant which is taking off.
No, and this peak came because of a new variant on February 1st.
Right.
Yeah, that's right. Yeah. All on the same scale, yeah.
But it's on the same scale.
On the same scale, yeah.
So those fatalities which occurred due to the first variant, for instance, they dive down,
yeah.
And now there's a longer-lived variant which is now taking off.
Yeah.
Is that the reason for this?
Yeah.
peak?
So at this time, about 35% of population is still susceptible.
Right.
And in that time, if you introduce a new variant which is twice as more infectious than the earlier one, plus you allow people to intermix freely, you get another wave, another peak.
Oh, I see. The second variant has not been present from the beginning.
No,
It's not. Yeah. It's introduced at that time.
It's introduced at that time, yeah.
I see. Okay.
I mean, that was our understanding that in Akola and Amravati in early January, there were a lot of interactions, marriages, and that's how this...
okay.
Yeah, we don't exactly know how Delta started. Yes.
So you basically talked about scaling up of the models.
Scaling of the?
Yes, using the small model.
That's right. That's right. Yeah.
Are both populations having the same exponential?
So how do we kind of match the two? So in a 1 million model, we have 13 times less number of homes, but within the home, the structure is identical to the earlier one. 13 times less workplaces, within workplace, the structure is similar. Community is the same number in larger and the smaller model, but in community, in the larger model, one person who's infected will infect another person with some rate. In a smaller model, that person is infected with a larger rate. So total number of people I'm infecting in a community, it's, number of people times the probability, it becomes a Poisson process. So the Poisson rate is unchanged. So number of people each person infects in a community in a smaller or larger model remains the same.
Yeah, nice talk, Sandeep. So one question, looks like from a predictability standpoint, the model did well. From standpoint of analyzing interventions, how would this model do? One, which seems to, because the second question, which I didn't understand very well, is this notion of shifting on the time of the intervention. Is it a fitting process, or, let's say we have an intervention that happens, how do you decide how much of the shift on that intervention to be done to get it right?
I think the upper point is clear that we can only go up to, sorry, I'll just go down. So this point, day 35, is essentially log of n divided by log of rho. N is the overall population and rho is the exponential rate of growth. So that's a calculation that just comes from there. So that point is fixed, so you can't go beyond that. So I'm going to take this point and match it to a point below. So this point I can't take above 35 days. Maybe 36, 37, but no more than that. This point I could have gone all the way up to day 15 or day 10. But this I'm just speaking empirically. I don't have any mathematical basis for it. Empirically, we saw that we could have gone down further a little bit more. Here, it's more of a fitting in some sense. But I mean, it's clear what we are looking for. At this point, also, we want the branching process proportions to have stabilized. So that's all we are looking for, and that seems to work out. You can see empirically early on in 10-15 days.
Do you think that, just a quick, sorry, do you think that the branching process worked well partly because of the density in Mumbai, or if you have a much sparser network to begin with, the branching process, you intuitively think that the density would have some role in the quality of this branching process?
Yeah, so I should say, we've not been able to test it. That's a fair point, because you could say that the mean field behavior, because with lockdowns we reduce mobility. So that corresponds to maybe having a larger city which is more spread out with less mobility. So that's showing that the mean field behavior is fairly robust. It would have worked even in a much larger, much more spread out city. But for branching process, I can't say because there's no test case per se. It's worth checking. I don't expect it to be very significantly different, but yeah, it's worth checking. Now, your other question was how did we do vis-a-vis interventions? Right. This is at the time, because we have kind of stopped doing. I mean, all we are saying, predicting forward is okay. This is when the peak will occur, when this will occur, and those are robust even to interventions by and large. So we could say, for example, that if there was no lockdown, then this peak that we saw in April would have been delayed by about a month. So those kinds of things we could say, and that we would not be too off by doing that. Yeah, at this time it was very interesting. We were talking to the BMC municipal commissioner. This is now in May this year, and we barely understand what we are doing. And then he looks at our chart and says, everybody else is saying cases are going to go up, but you are saying the cases will come down, because that's what the model was saying. Model was saying this will come down over here, and we said yes. And we were very scared because at the end this is just computer output. We don't know what's going to happen. So that became a test for us if there's something predictive in the model or not. And eventually it did come down around that time. That was very useful for us to see. So yeah, probably got lucky or something a few times.
I have a question related to the rapid spreading during Delta wave. So you said that it could be the variant of virus.
Can you repeat and louder?
Okay, I have a question regarding the rapid spreading during Delta wave.
Okay, rapid spreading, yes.
So you said that it could be the virus is more infectious.
Yeah.
So if the virus is continuously mutating during every replication, do you think that it is possible that the faster spreading ones or the more infectious ones are preferred or survived during, then that causes this kind of a super spreading event?
Well, that was kind of your question, that at this time, if you just had variant which spread at the same rate as the Wuhan variant, then the disease had already died down. But with the same population, with almost the same kind of mixing, you have a variant which is 2.5 times more infectious, 2 times more infectious, suddenly things take off all over again. And that's how things happen in real life, and that's stimulation model captures that.
We'll take one last question. Yeah.
No, the equation, one thing I didn't understand, if you go back to the mean field equation, the SIR model or related models, and you scale everything in terms of the total population size, then there's only one parameter, which is the reproductive ratio. And so whether it's million, 10,000, etc., once you do that scaling, all the curves will look the same.
Right.
So I was just wondering whether that is if you plotted the y-axis not in terms of the scale but the absolute numbers, then you will see the larger population take off faster and the smaller population take off slower. But if I divide by n, they're actually the same number because the underlying equations are the same. So I was just wondering whether this shift is really the underlying reason for your ability to shift.
Let me understand what you're trying to say.
So I have a comment on that actually, because you're doing agent-based models and Gautam is doing compartmental. They are actually the same if you have infinitely well mixed in that every agent talks to every other agent.
Lots of compartments,
in Bombay where your chaiwala talks to somebody in IIT Bombay who talks to somebody in Bandra. I mean, everybody talks to everybody. Then the two models are exactly the same, and that's not the case. So I also did some simulations back then, which was there in the preprint. Essentially, if your Bombay had everyone talking to everyone, then I think the compartmental model thing will work, and the scaling according to that will work. What you're doing is scaling.
So you're telling me then, okay.
I'm asking if I understood what you said. The family structure stays the same, the office structure stays the same, but the number of families, the number of offices changes. So it's a rather complicated scaling of the network structure of the model itself. So it's not obvious what the scaling is. You're doing it kind of empirically, if I understand right. I mean, as in you are calculating how many people infected going backwards, when that many people infected, matching that data and all that.
Let me just understand. You're trying to say somehow that whatever I've said would have been reproduced by a compartmental model. Is that?
If it was a well-mixed system, then it could be reproduced.
I mean, Mumbai, that's the strength of Mumbai. It is a well-mixed system. Huh?
You don't talk to everybody in Mumbai. If you actually had contact
No,
with the other
that's a very narrow mathematical assumption. If I talk to A talks to B talks to, it's a small world. After a while, everybody talks to everybody, and you can prove theorems that way too.
Yeah, can we just have it after that? So we'll just move.
No,
to
I'll just make one quick point that it's correct that, in some sense, what we have is after the initial random phase of branching process, once you get a handle on the randomness, and there's a one single random variable, thereafter it's a deterministic evolution. We capture that deterministic evolution in the mean field in a slightly complicated mean field, but it's basically like a compartmental model. And maybe a simpler model would approximate it equally well. That part is correct. But currently the way compartmental models are working, they're only looking at the deterministic phase. They're ignoring the initial stochastic phase. So in some sense, we combine the two together, and you could say that maybe there are clever ways or simpler ways of combining these two, and that's worthwhile activity. I think that would be worthwhile research. Yeah.
So I see few other raised hands. We can probably do that after the break, during the break. So let's thank Professor Juneja once again.
Thank you.